Hey everyone, welcome back and let's write some more neat code today. If you are afraid of dynamic programming problems, I promise by the end of this video you're going to realize that it's actually not so bad. So let's get into the problem uncrossed lines. We're given two integer arrays nums1 and nums2, and then they continue to give us this story. But if you've been watching my videos, you know I really don't care about these stories at all. They just overcomplicate things for us. So let's keep it simple. Sometimes I just skip the description and just go immediately to the example and then come back to the details in the description. I think that's one good technique for quickly understanding what a problem is asking for. Let's say this is one of our arrays and this is another array. The idea is that we can find matching characters between the two arrays. So as you can see, these two characters match each other. There's also a 4 over here and a 4 over here. And also there's a 2 over here and a 2 over here. So it looks like there's 3 matching characters between the two arrays. So is that what we're trying to do? Just return the total number of matching characters? Well, not quite. It can't be that easy. We are not allowed to choose both of these matching pairs because they cross each other. We can choose these two. We can choose this pair, but then we can't choose this pair because notice how they cross each other. The index of this guy is less than the index over here, yet the guy over here is greater than the one over here. So that's how we know that we have a line crossed. Once we have this matching pair, we pretty much have to say that any additional matching pair we find has to come somewhere to the right, not only of this, but also of this. So everything to the right over here. Now, this is definitely not a simple problem, especially the way they set it up. This problem description is something out of a horror movie, to be honest. But when you get stuck on a problem like this, you don't just want to stare at the problem. You want to try things, even if it's something really naive. I mean, maybe a hash map is going to work here. Well, you're going to quickly realize that a hash map's not going to do anything for us here. But that will take you one step closer to the solution. Now, the first observation here is that we probably have to look at every single value here and probably every single value here. It probably doesn't matter whether we start at the left side or at the right side. We're going to have to go either from left to right or right to left. It doesn't matter, so I'm just going to start all the way at the left. Now, as we continue iterating, we might have obvious choices for us. Like, obviously, these two guys match each other. So at this point, we can forget about this and just say that this is our new problem now. This is the new sub problem. And we just want to take a +1 from over here and then add it to the result of this sub problem. Now, we might get to a point where we do have choices. These two characters clearly don't match each other. We're looking for a matching pair. I guess one way in the future, as we keep iterating, we might find this matching pair, or we might find this matching pair. Now, in this case, it doesn't matter which one of these choices we choose because the result is going to be 2 either way. We can only choose one of these matching pairs. But take a look at another example. This is a technique you should try because sometimes the single example that Leetcode gives us isn't sufficient to actually identify how to solve the problem. So I'm going to add a 2 here and a 2 here. Now, there is a clear single choice that we should make. We should say that the 2 matches the 2 and this 2 matches this 2 and we get a result of 3. If we didn't do that, and we chose the 4, then we would never be able to choose these 2 matching pairs and we'd get a result of 2, which is definitely not the maximum. So at this point, we kind of realize when we're here, we don't know which choice is best. We can't predict the future. So we actually have to consider both choices. We have to say, maybe we want to find a matching pair for this 4, maybe. Or maybe we want to find a matching pair with this 2. We have to consider both cases. That's kind of what leads you to the brute force recursive solution. And to take it one step further, you might either realize this right now, or you would probably realize it as you code up the brute force solution. If you've already seen another problem before, it's another common dynamic programming problem. It's very famous. It comes up a lot in Leetcode. It's called the longest common subsequence problem. And that's exactly what this problem is. Instead of being given strings though, we are given arrays. It's pretty much the same exact problem because notice, they are essentially asking us for a subsequence of characters from both arrays. Like this is a subsequence. We say 1, skip the 4, 2, 2. We get a 1 here, 2, 2, skip this 4. These are both subsequences. If we were to try to include both of the 4s as well, we see that the two subsequences are definitely not the same. Remember, order matters in a subsequence. We are allowed to skip characters, but we can't change the relative order of elements. And if we wanted to include these 4s, we can't change the order. And clearly, these two do not match each other, so we have to skip the 4. So if you're good at dynamic programming, at this point, you probably know how to solve this problem. If not, I've got you completely covered though, and I'll show you exactly how we can take this from a recursive approach to the optimized dynamic programming memory approach. The first thing is, how do we formulate this as a brute force problem? Because it's not super easy the first time. Well, remember, it's all about choices. We're going to start at the beginning of both arrays. Probably we should do that with 2 pointers. I'm going to say I pointer is going to be for the first number in the first array, and the j pointer is going to be for the first number in the second array. And of course, we're trying to look for matching characters. It could be possible that we're just given 2 arrays that are the exact same, like 1, 2, 2 and 1, 2, 2. In that case, we just go character by character, say they match each other, and just keep incrementing our total count, and our life would be pretty easy. So in this case, that's exactly true. These 2 characters match each other. So now we are going to take our pointers, I and j, and increment them to be at the next positions now. In terms of our decision tree, we didn't really have to make any decisions. We started at 0, 0. I say 0, 0 because that's what the values of our pointers are. And we didn't have to make any choices. So here in our decision tree, I'm not going to draw 2 branches. We really only need 1 branch because then we got to a new subproblem, which was 1, 1. Here, though, things are going to get interesting because these 2 characters do not match each other. Now we do have 2 separate choices to make. We can either try to find a matching character for 4, in which case we would take the j pointer and increment it by 1 to be in the next position. So that would look like this. In our decision tree, we would say the new subproblem is 1, 2, because our j pointer was incremented. The other case is if we want to increment our I pointer because we're looking for a matching character for this guy. So in that case, our new subproblem would be 2, 1. Well, you might be thinking, what about the case where we maybe want to skip both of these characters? Maybe there's just not a matching pair for either of them. You're right. We definitely want to consider that case where we just go to the next position. But believe it or not, this current decision tree will handle that case because notice, if we find no matching characters in this subproblem, then we'll branch again. We'll branch to this part where we go to 2, 2, and we'll branch in this direction where we go to 3, 1. So this solution is exhaustive. It's definitely going to find us the solution, but it might not be super efficient because notice in the worst case, we might be branching 2 times on every level, and overall the height of this tree is actually going to be the sum of the length of the first array plus the length of the second array. The reason we have to add both of those together is because in the worst case, we might only increment 1 of the pointers at a time. Every time we go down 1 level in our decision tree, we might only increment 1 of the pointers. So the overall time complexity of the brute force approach is going to be 2 to the power of, let's say, m plus n, where these are the respective lengths of the 2 arrays. I made this tree a tad bit smaller because I want to continue drawing on it because I want to show you that some of these subproblems, which are going to be recursive calls into our recursive function, these repeat themselves. Watch. It could be possible that for this position, we don't find matching characters. I think in our case, we might actually, but in some problems, we might not. So we might draw a decision tree that looks like this, where here we go to 1, 3, and over here we go to 2, 2. And now we notice our first subproblem has repeated itself. This is our first repeating subproblem we found in our tree, but there could be many, many more. You can imagine that as these trees get really, really large, we might make the same recursive call multiple times, ending up, which causes us to do repeated work. We want to eliminate all of this repeated work. We should only have to call the recursive function with these parameters a single time. So once we've computed the result, we're going to cache the result of the recursive call into a data structure. What I usually use is a hash map, but I think sometimes you can also use a two-dimensional array depending on the dimensions of the dynamic programming problem, which brings us to kind of the important part. What are the variables we're going to use to actually cache subproblems? How do we even identify a subproblem? Well, notice I only drew 2 values at every node of this tree because we only need 2 parameters, and those parameters are our pointers, I and j. They determine what subproblem we are currently trying to solve. And at this point, I could keep talking and talking and talking, but why don't I actually show you the code for this solution as well as the time complexity? So remember, we want to do this recursively, so I'm going to define a DFS function. You could call it something else like helper or something, but the important thing is that it only takes 2 parameters, I and j. Now, this is recursive, and I didn't really talk about the base cases in the drawing explanation, but you can imagine the obvious one here is when we go out of bounds of one of the arrays. So if our I pointer goes out of bounds, which would mean I is equal to the length of nums1, or if j is equal to the length of nums2. In that case, if one of them is out of bounds, of course, they're not going to have any matching characters between them, so we can just go ahead and return 0. Otherwise, we're going to continue. The first question we probably want to ask is, does the character at position I in nums1 match the character at position j in nums2? That's going to be one case, and the other case is going to be if they do not. So if the characters do match each other, what is going to be the number of matching characters? Because that's ultimately what we're trying to determine. Well, it's going to be 1 because we just found a matching pair, plus the result of the subproblem, which is going to be DFS on I plus 1 and j plus 1, just like I talked about. Now, the other case is if they do not match each other. This one's a bit more complicated because we do have to branch. We have to call DFS 2 times. And the first time we call it, let's say we just want to increment pointer I and leave j the same. The second time, maybe we want to leave I the same and increment j. But whatever these two return, we want to return the maximum of them because that's what we're trying to do. We're trying to find the max uncrossed lines. So this is the brute force approach to do exactly that. I guess these are short enough that I can put them on one line. Now, in the brute force solution, I would just put a return statement here and a return statement here. But if we want to add caching to this solution, let's declare our data structure, our cache, and let's declare it outside of the scope of this function so we have access to it. What I usually do is try to keep it simple if I can. And in this case, we can just use a hash map. So that's what I'm going to do. You could also use a two-dimensional array because we just have 2 values that decide a subproblem. The number of possible values I could be is the length of nums1. The number of possible values j could be is the length of nums2. Like the total number of unique combinations the parameters could be is going to be the length of nums1 times the length of nums2. That's why the space complexity of this problem is going to be n times m, where these are the dimensions of the 2 arrays. So that's why we would use a two-dimensional array, and that's why the size of our hash map is going to be this in the worst case. Now, we're going to add another base case. What if we've already solved this subproblem before? What if this key already exists in our DP hash map? If it does, then we can just return the value that's stored in the hash map corresponding to that key. But if it's not, if it doesn't already exist, then we have to compute this value, and we're already doing that below. We just aren't storing it in the cache, so let's do that. Let's say dp is equal to this, or dp is going to be equal to this, but regardless of which one of these executes, we want to return the value that we ended up computing. So now the only thing left for us to do is actually call our DFS function, and we're going to start at the beginning of both of the arrays so we can pass in 0, 0 and then return the result of that. And I'm going to run this to make sure that it works, and thankfully it does. But at first, it looks like it's not very efficient. That's a little bit misleading because the time complexity of this approach actually is big O of n times m. That's actually about as efficient as we can get it. And the reason that's the time complexity is because that's the number of unique times that this DFS is going to be called and fully executed. And on each recursive call, it's not like we have a loop inside of it. So each call will pretty much run in constant time. At least we can kind of assume that for our calculation. So that's how we get this time complexity from. This is the memoization solution. Now let's try to understand how we can actually solve this using the true tabulation dynamic programming method, which, if you're not familiar with it, is basically a way to solve this problem without recursion. We noticed that there are subproblems. We noticed we started at this problem, but recursively, we break it up into these types of subproblems, but recursively, we take smaller subproblems. We can do the same thing without recursion. Now that we know the dimensions of this problem, I've taken a grid and created it based on the length of this array and the length of this array. And let's say I'm going to take this and draw it along this axis, just like this, 1, 4, 2, 2, and I'm going to take this and draw it along this axis, 1, 2, 2, 4. Now you might be thinking, why is the size of the grid a little bit larger than it actually needs to be? Well, you'll see in just a second, it has to do with an edge case. You might not know that like the first time you're trying to solve a problem like this, but as you get pretty deep into the code, you do realize the dimensions could be larger, and that makes the problem a little bit easier to code up. But what exactly does a position in this grid represent? Well, let's start with this position because it's simple. This position represents the longest common subsequence, because remember, that's what this problem is about, LCS. It represents the longest common subsequence between these two values. What would that be? Well, they're exactly equal to each other, so the result is going to be 1. Now, an arbitrary value like over here represents the LCS between this prefix of the array and this prefix of the array. What does that happen to be? What is the LCS between these two subarrays? I don't know. Do you? Well, how exactly can we calculate it? The first step might be to compare the two characters, right? These two characters are both equal to 2, so they equal each other. Well, that tells us there should at least be a 1 value over here. But now what? We can only look at one character at a time. Is it possible that maybe we could pre-compute some subproblem and then use the result of that subproblem to save us time? Yes, that's exactly what we're going to do. As you can tell, if this character equals this character, then the new subproblem is basically asking what's the LCS between this prefix and these two characters, and take that and add it to the one matching character that we already found. Okay, well, where would the result of this subproblem be stored? Probably over here. So what we're saying is, if we want to find the value that should be stored here, we can say 1 because these two characters match each other, plus whatever value is stored over here. Perfect, right? So that kind of hints to us what order we should pre-compute this two-dimensional grid in, because that's what dynamic programming is all about. Pre-computing problems in a certain order to save us time. And after we have done all of that, we know that our result is going to be stored in this bottom right corner, because this value would tell us the LCS between this and this. Now, there's one last thing to mention, which is what happens when the two characters do not match each other. 2 does not equal to 4. So we're not actually looking for this subproblem anymore. We are actually looking for this subproblem, where we say we're trying to find a matching character for 2, so we just decide to skip this 4, since it didn't match with the 2 over here. So we could decide to skip the 4. Where would the result of this subproblem be stored? Probably over here, right? Because look at this, and then look at that. So that's one possible case. Another possible case could be that we want to actually skip this 2. So since this 2 didn't match with this, we're going to decide to skip this one. And now this is the new subproblem that we're looking at. Where's the value going to be stored? Probably over here, because it corresponds to that and that. So basically what we learned here is if we want to find the value stored here and these two characters don't match each other, we're going to look to the left for what value is stored over here, and we're going to look above for what value is stored over here, and we're going to take the maximum of those two and store that in the position over here. Okay, to summarize, to compute the value in a position like this, we might have to look to the left, we might have to look up, or we might have to look diagonally. So in what order do you think we should solve the subproblems in? Probably in this order. Very straightforward, just like you would fill in a two-dimensional grid, because if we have, like, let's say all of these computed and we're trying to find this one, look at this. We have the guy on the left, we have the guy up above, and we have the guy at the top left. So this is the perfect order to compute these subproblems in. And lastly, the reason that the dimensions are larger than they need to be is because when I initialize this grid, I'm going to initialize it with all zeros. And when we get to the first subproblem over here, these two characters match each other. So what we're going to do is try to look to the top left. If we were trying to do that and we were over here, what would happen? We would go out of bounds, wouldn't we? So that's why I have some extra space over here, which is just going to be filled in with a 0. Same with this row and same with this column. Okay, now finally, let's code this up. And by the way, you can kind of tell that the time complexity is still going to be the same. Obviously, the space is going to be n times m. And since we're filling in the grid, that's going to be the time complexity as well. Okay, so now getting into the DP solution, the first thing you might think you'd want to do is initialize your two-dimensional grid, right? And that's a perfectly good strategy, but for me, I find that we don't quite know how we want to use our grid before we actually try to code up the algorithm. So I try to actually code it up before I initialize the grid. That also kind of helps you realize if you actually need to add that +1 to avoid the index out of bounds error. So what I'm going to do now is say for I in range the length of nums1 and a second loop for j in range length of nums2, we're going to pretty much check the exact same thing we did in our recursive solution. We're going to check, does the number in the first array match the number in the second array? There's also the else case as well. Now, first, if the characters do match each other, we probably want to do something like dp at I and j is going to be equal to 1 plus dp at I minus 1 and j minus 1, right? Because isn't that how we look diagonally to the top left? You're right, but remember, I is going to start at 0. J is going to start at 0. If we try to do I minus 1 and j minus 1, if we try to do 0 minus 1, we're going to get an index out of bounds error. So the way I'm going to use this DP two-dimensional array is I'm going to add 1 to it every time we try to use an index. So the equivalent of that would basically be just adding 1 to each of these and getting rid of the -1 from here and getting rid of the -1 from here. And once you get to this point, it'll be kind of obvious. And that's kind of how you would know you'd want the dimensions of the grid to be +1. And since we kind of see now how we're using the I pointer here, I is going to correspond to the row, j is going to correspond to the column. So now we can kind of initialize this and kind of know what we're actually doing. We don't have to guess what the dimensions are going to be. So the first row is going to be multiplied by the length of nums2 plus 1. And the number of rows are going to be the length of the first array. So for underscore in range length of nums1. This is just a two-dimensional array filled with all zeros. And actually, when we say length of nums1 here, we should add that +1. That's very important. We don't want to get an index out of bounds error. And finally, let's go ahead and fill in the else case. It's going to be pretty similar. We're going to want to assign I +1 and j +1, but we want to make 2 recursive calls in this case and find the maximum of both of them. Well, I forgot we're not doing recursion anymore, but we want to find the 2 values stored in our grid. At I, we'd normally say -1, but we already have the +1 here, so we're basically just getting rid of the +1 and leaving j +1 the same. Or we would take dp of I +1 and then leave j the same. So this is taking the maximum and assigning it into our dp. And after all of that is done, remember where our result was stored. It was stored in the bottom right corner of the grid. So we're going to say length of nums1 and length of nums2. Now I'm going to run this to make sure that it works. And as you can see, yes, it does. And I guess it's a bit more efficient, even though the time complexity is the exact same as the recursive solution. Now, lastly, there's one little optimization we can make. The memory complexity of this is O of n times m. But we can actually condense the memory complexity to, instead of using the grid, we can just use a single row from this grid, I think M corresponds to nums2. So the length of one of our rows is the length of nums2. So let's say the memory complexity then would become big O of M. But how exactly do we do that? Well, let's go back to the drawing board for a second. Remember, every time we want to compute a value like over here, we only have to look possibly to the left or up above or to the top left. So by the time that we get, let's say, all the way down here, do we really need this entire row in memory? Do we really need this entire row in memory? No, we do need this row in memory because from here, yes, we might try to look up, we might try to look to the top left, we might try to look to the left. We need this row in memory as well. But clearly, we only need up to 2 rows in memory at a time. Why would we need to have extra memory if we aren't actually ever going to need it? And that's exactly the trick to optimize the space for this problem. We only keep 2 rows at a time. Our first row is going to be a bunch of zeros. Our second row is going to be the one that we're currently filling in. As we fill in these values and we finish the row, we realize the next row we want to fill in is down here. And to fill this row in, we do not need this in memory anymore. So we basically get rid of it, or at least reassign it. So knowing this, let's try to optimize the solution. Up above, I'm just going to take this 2-dimensional array and transform it into a single array, or a 1-dimensional array. It's filled in with all zeros. I'm going to move this comment up above. And now this is going to be a little bit tricky. Basically, on each iteration of the outer loop, we are going to try to fill in a new array. I'm just going to call it new DP. I don't know a really good name I could put for this, but let's say this is going to be the same dimensions as this. So I'm just going to copy that. And then since this is the one that we're actually trying to fill in, let's start replacing these 2 assignments. The first one should now be new DP at position j+1, we can probably still use j+1 here, is going to be equal to 1 plus this DP is accessing the previous row. So we consider this to be our previous row. So we're going to say DP at j, just like using the same j here. And to make this a little bit more clear, let me actually update the variable names, changing dp to be previous. So that's going to be previous, and this is going to be previous. And this new dp, let's just call it a dp. So this is also now going to be changed to dp, and we can get rid of this line. So this is basically doing the same thing. If we find matching characters, we want to look up above and to the left. That's why we changed the j+1 to a regular j. And for down here, we want to do something very similar. So dp of j+1 is what we're trying to determine yet again. But we want to take the maximum of the value to the left, which is going to be dp of just j. So staying in the same exact row, looking to the left of this value, or looking up above in the previous row, which is previous at position j+1. In this case, j+1 stays the same because we're not moving to the left. We're just looking up above. Now, after that is computed, we know that dp will store the result in the last value of that array. So we can say dp at length of nums2 is going to be our return value. Now, there's just one last thing, and that's we have to kind of update the previous and dp arrays. After we compute the current DP array, we should say that previous has become the DP array. And on the next iteration of the loop, we're going to create a new DP array so that we can fill that guy in using the previous one. And then by the time this loop is actually finished, the result will be not stored in DP, but it will actually be stored in previous. That was my bad. Sorry about that. So now I believe we can take this and run it to make sure that it works. And as you can see, yes, it does, and I guess it really is the most optimal solution. If you found this helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. It has a ton of free resources to help you prepare. Thanks for watching, and hopefully I'll see you pretty soon.